This online tutorial is about the acid-base strength. In context of acids and bases, acid-base strength is a very important concept. We've already discussed different acid-base theories, and we've seen that while different acid-base theories have different definitions, they are all similar in the fact that acids are donors of positive species or acceptors of negative species, while on the other hand, bases are acceptors of positive species or donors of negative species. In none of those acid-base theories, all molecular entities or chemical species behave equally. Different chemical species have different acid-base behaviors. In any of those acid-base theories, some chemical species behave as acids, some chemical species behave as bases, some chemical species behave neither as acids nor as bases. In addition, among acids, abilities and tendencies to act as an acid are different. Also, among bases, abilities or tendencies to act as a base are different. Such differences play important roles in acid-base phenomena, like direction and extent of acid-base reactions. Therefore, it is essential to pay attention to such differences. In literature, the common terms for ability or tendency of a chemical species to act as an acid are acidity, also
acid or acidic strength.
On the other hand, the common terms for ability or tendency of a chemical species to act as a base are basicity, also
base or basic strength.
For example, IUPAC considers acidity of a Bronsted acid as its tendency to act as a hadron donor, a proton donor. On the other hand, IUPAC considers basicity of a Bronsted base as its tendency to act as a hadron acceptor, a proton acceptor. As another example, Lewis acidity refers to tendency of a Lewis acid to form Lewis adducts by accepting an electron pair from a Lewis base. On the other hand, Lewis basicity refers to tendency of a Lewis base to form Lewis adducts by sharing an electron pair to a Lewis acid. So we see that expressions like Bronsted acid A is stronger than Bronsted acid B, or acidity of Bronsted acid A is higher than that of B, or acidic strength of Bronsted acid A is higher than that of B, and so on, all refer to the fact that Bronsted acid A is a better acid than Bronsted acid B, or the tendency of the Bronsted acid A to act as an acid is higher than that of B. Acidity or basicity can be expressed both qualitatively and quantitatively. A qualitative expression gives an order of relative strengths, like acid A is stronger than acid B is stronger than acid C, and so on. For example, if Bronsted acid A can protonate a base, while Bronsted acid B can't do so, we can say Bronsted acid A has higher acidity than Bronsted acid B, or it is stronger. It has more ability or tendency to act as an acid. A quantitative expression or measure gives numerical values for quantities whose values are related to or quantitatively measure acidity or basicity. Like always, quantitative measures include qualitative measures, and in addition, quantitative measures are usually much more powerful than qualitative measures. So quantitative measures are important in the context of acid-base strength. There are several common quantities to measure acidity or basicity. But before we proceed to such discussions, we should consider a very important point in this discussion. Whenever we want to consider a quantity to measure acidity or basicity, besides its numerical values, we should consider other aspects of the phenomenon. Let's discuss it in this way. Whenever we consider a quantity to measure acidity or basicity, we should consider the free watts in the following sentence. Okay, so we are focusing on acidity and basicity concept. In this concept, this is important. It measures watt for watt at what situation? These three watts are important. We should pay attention to them. The first watt points to the quantity used to measure acidity or basicity. What type of quantity is it? What properties does it have? To quantitatively measure acidity or basicity, we usually use thermodynamic quantities like delta H, enthalpy change, delta G, Gibbs energy change, K, equilibrium constants. These quantities have different properties, and we should pay attention to those differences. For example, enthalpy change doesn't include entropic effects, delta S, while delta G and K also include entropic effects. So, for the cases where entropic effects are important, delta H will be unsuitable, and it would be better that we use delta G or K. The second watt here points to chemical species under analysis. Is it an acid or a base? Is it a Bronsted acid, and are we measuring its hadron donating ability, or is it a Lewis acid and are we measuring its electron pair accepting ability? And questions like this. Here, another important point to say is the fact that we can consider and measure acidity and basicity for both compounds and mediums. For example, we may wish to measure acidity of acetic acid, CH3COOH, in aqueous solutions by measuring related equilibrium constants. Here, of course, since equilibrium constants are independent from concentrations, concentration will not be a factor, it will not be important. On the other hand, if we wish to measure acidity of a 1 molar acetic acid aqueous solution, and compare it with the acidity of a, for example, 0.5 molar acetic acid aqueous solution, then concentration will be important. So we may measure acidity or basicity for a compound or for a medium, and there are differences between them. The third one here points to the situation at which measurements are made. When situations at which measurements are made change, acid-base behavior of chemical species change. These changes can range from negligible change to dramatic or decisive change. For example, when acid A is stronger than acid B in a given situation, we usually expect that not only both of them, A and B, remain acids in other situations, but also in other situations, acid A acts better as an acid than acid B. While, of course, this is the case for many situations, for many cases, there are cases in which the behavior of a chemical species changes from acidic to basic when situation changes, or cases in which relative acidic strengths change when situation changes. For example, at situation 1, A is acid, at situation 2, A is a base. Or, as another example, at situation 1, A is a stronger acid than B. At situation 2, B is a stronger acid than A. So situation is very important here, and we should pay attention to see at what situation we are measuring acidity or basicity. One important point in this regard is the fact that we are measuring acidity or basicity in gas phase or in a non-polar solvent or a polar solvent. In gas phase, we don't have any solvation effect. We don't have any solvation, where solvation refers to interactions between solvent and solute molecules. But in nonpolar and polar solvents, we can have solvation effects. We have solvation. In polar solvents, solvation effects are usually important and we usually can ignore them. But in non-polar solvents, solvation effects are usually small and negligible, and so we can ignore them. In gas phase, we are sure that we don't have any solvation effects. So we can state that measurements in gas phase show inherent acidity or basicity. They just focus on the chemical species, on the analysis, while measurements in nonpolar or polar solvents may get affected by solvation. And also solvent may play an important role. So in the context of acidity and basicity, it is important that we pay attention to these three what's. Bronsted acid-base theory is very common in the context of acids and bases. Bronsted acidity refers to tendency of a compound to act as a hadron donor, and Bronsted basicity refers to tendency of a compound to act as a hadron acceptor. Quantities for measure Bronsted acidities or basicities deal with reactions in which we have addition or removal of H+, hydrogen cations, hydrogen ions. In literature, the common quantities to measure Bronsted acidity or basicity are acidity constant, Ka, protonation constant, Kh, basicity constant, Kb, proton affinity, Pa, gas phase acidity, gas phase basicity, and acidity functions. I'm going to discuss these quantities. Acidity constant, Ka, also called acid dissociation constant, and also acid ionization constant, is very common to measure acidity and basicity. Ka, acidity constant, is the equilibrium constant for splitting off H+ from a Bronsted acid. For example, Ka for acetic acid in aqueous solutions is the equilibrium constant for this reaction. Acetic acid reacts with water to yield acetate ion and hydronium ion in aqueous solution. We usually simplify this to this reaction. As far as we consider that we can have alone H+ ions in solutions, H+ ions in solution are always solvated. So for simplicity, we consider this reaction instead of this. Ka of acetic acid is the equilibrium constant for this reaction. Ka is in fact a thermodynamic equilibrium constant, and it should be written in terms of thermodynamic activities. But for simplicity, we use concentrations instead of activities, and we consider concentration equilibrium constant instead of thermodynamic equilibrium constant. So here, for simple discussion, we consider Ka of acetic acid in aqueous solutions as follows. Ka equals the equilibrium concentration of acetate ion times the equilibrium concentration of H+ divided by equilibrium concentration of acetic acid. Its value at 25 degrees Celsius is 1.75 times 10 to the minus 5. Here, X in brackets refers to the amount of substance concentration, or simply amount concentration of X, which is amount of X divided by the volume of solution. Its unit is, the unit for it usually is mole per liter. In literature, it is common to call it molarity, but IUPAC discourages the usage of molarity due to possible confusion between molarity and molality. As another example, we can consider Ka of ammonium NH4 plus ions in aqueous solutions. Ka of ammonium aqueous solutions is the equilibrium constant for this reaction. Here, Ka equals the equilibrium concentration of NH3 times the equilibrium concentration of H plus over the equilibrium concentration of NH4 plus. And its value equals 5.6 times 10 to the minus 10. Sometimes values of Ka are reported in the form of pKa. pKa is the negative decimal logarithm of Ka. Or in fact, it is the co-logarithm of Ka, as co-logarithm is the negative logarithm in the base 10 of the base 10. Based on this reaction, Ka equals 10 to the minus pKa. For example, pKa of acetic acid is the negative decimal logarithm of this number, which equals 4.756. On the other hand, pKa of ammonium ion is the negative decimal logarithm of this number and equals 9.25. On the other hand, Ka of acetic acid is 10 to the power of minus this number, and Ka of ammonium ion equals 10 to the power of minus this number. When tendency of a Bronsted acid to act as a hydrogen donor increases, its acidity gets higher, this chemical equilibrium shifts to the right, to the side of products. So value of Ka increases. On the other hand, when Ka increases, due to this minus sign, the value of pKa decreases. So we see that higher values of Ka or smaller values of pKa are associated with higher acidities, stronger acids. For example, here, Ka of acetic acid is greater than that of ammonium ion. On the other hand, its pKa is smaller. So we can conclude that acetic acid in aqueous solutions is stronger than ammonium ion. Protonation constant, Kh, is a quantity to measure basicity of Bronsted bases, and it is closely related to Ka. Protonation constant is the equilibrium constant for reaction in which a Bronsted base accepts an H plus. For example, protonation constant Kh for acetate ion, the conjugate base of acetic acid, is the equilibrium constant for this reaction. As another example, KH for ammonia, the conjugate base of ammonium, is the equilibrium constant for this reaction. In aqueous solutions, of course. Similar to pKa, we can consider pKh, the negative of decimal logarithm of kH. It is easy to see that for a conjugate acid-base pair, like acetic acid and acetate ion, or ammonium ion and ammonia, Ka and Kh are reciprocal of each other, as these reactions are reverse of each other. So, if Ka of acetic acid equals this number, Kh of its conjugate base is its reciprocal. And of course, its pKh will be minus this number. On the other hand, if Ka of ammonium ion is this number, Kh of its conjugate base will be this number. It's reciprocal. Kh is a measure of Bronsted basicity. Higher values of Kh show greater tendencies to act as a hadron acceptor, act as stronger bases. So we see that higher values of Kh or smaller values of pKh means stronger bases, higher basicities. Since these two quantities are reciprocal of each other, when one of them increases, the other one decreases, and vice versa. So we see that acidity and basicity of a conjugate acid-base pair are reverse of each other. When acidity of a conjugate acid increases, the basicity of the conjugate base decreases, and so on. For example, acetic acid as a Bronsted acid is stronger than ammonium ion. On the other hand, the value of Kh of NH3 is greater than that of the acetate ion. So among conjugate bases, ammonia is stronger. Weaker conjugate acid has stronger conjugate base. Another closely related quantity to these quantities is Kb, basicity constant. Basicity constant, Kb, also called base dissociation constant, base ionization constant, is the equilibrium constant for the reaction in which a Bronsted base accepts an H plus from a solvent molecule. For example, Kb for acetate ion is the equilibrium constant for this reaction. And Kb here equals to the equilibrium concentration of acetic acid times equilibrium concentration of OH minus hydroxide ion divided by equilibrium concentration of acetate ion. As another example, Kb for ammonia, the conjugate base of ammonium ion, is the equilibrium constant for this reaction. Their values are as follows. Similar to pKh and pKa, we can also consider pKb, where pKb is the negative decimal logarithm of Kb. Kb is a measure of Bronsted basicity. Higher values of Kb, smaller values of pKb show higher basicities, stronger bases. Like Kh, Kb is not reciprocal Ka. Kh is the reciprocal of Ka, but Kb is not the reciprocal of Ka. However, they are related to each other. We will see that the product of Ka and Kb in any solvent is equal to a constant called autoprotolysis constant of that solvent. So there are these constants, these equilibrium constants, are not independent from each other. Their values are related to each other. Similar to the discussion for Kh, when a conjugate acid gets stronger, its Ka value increases, the conjugate base gets weaker, its Kb value decreases, and vice versa. We can check this for acetate ion and ammonia. These three equilibrium constants are common to quantitatively measure acidity and basicity of Bronsted acids and bases. They are related to each other, and they are usually used in mediums. Usually the solvent is water, but also it is possible to consider other solvents. And we have measurements of these quantities both in aqueous solutions and in non-aqueous solutions. Proton affinity, Pa, is another quantity to measure Bronsted basicity. Proton affinity, Pa, is the negative of the enthalpy change for the reaction of addition of a free H plus in gas phase. For example, proton affinity of ammonia Pa is the negative of the enthalpy change for this reaction. And for ammonia, proton affinity is equal to 853.6 kilojoules per mole. As another example, proton affinity of water is the negative of the enthalpy change for this reaction. And it is equal to 691 in this case. You see that in proton affinity, we have addition of an H plus in its free form, in the gas phase, to a Bronsted base, the chemical species under analysis. These reactions are exothermic, they release heat. So proton affinity, which is the negative of enthalpy change, the proton affinity will be positive. Higher value of proton affinity shows greater tendency of the base for H plus. So higher values of PA, proton affinity, shows higher basicity, stronger bases. For example, here, ammonia is a stronger base than water since its proton affinity is greater than water. Proton affinities are measured directly or indirectly in the gas phase without presence of any solvent. So in the case of proton affinities, despite equilibrium constants, we don't have solvation effects. This is a great advantage for proton affinity, and proton affinity can be considered as a fundamental measure of inherent basicity, a measure without any solvation effects, a measure which is independent from solvent and only depends on the chemical species under analysis. Proton affinity has the disadvantage that it doesn't include entropic effects. But fortunately, there are many cases in which entropic effects are not important. The reverse of these reactions is the proton loss reaction, and it can be considered as a measure for acidity of the conjugate acid. Again, when basicity of the conjugate base increases, its proton affinity increases, we will see that the acidity of its conjugate acid, proton loss, for example, will decrease. For example, the reverse of this reaction will require less energy than the reverse of this reaction, meaning that hydronium ion in gas phase is stronger than ammonium ion, where on the side of conjugate bases, ammonia was stronger than water. We also have gas phase basicity, or absolute or intrinsic basicity. Gas phase basicity is the negative of the Gibbs energy change for this reaction, addition of a free H plus to our chemical species. For example, for ammonia, gas phase basicity, the negative of Gibbs energy change for this reaction equals 819 kilojoules per mole. As another example, gas phase basicity of water is the negative of Gibbs energy change for this reaction and equals 660 kilojoules per mole. Gas phase basicity has the advantage that it includes entropic effects. It is also free from solvation effects. So we can consider gas phase basicity as the best measure for for inherent basicity. Reverse of these can be considered as gas phase acidity. So gas phase acidity is the negative of the Gibbs energy change for a reaction like this in gas phase. A reaction in which we take a free H plus from our chemical species in the gas phase. So gas phase acidities and gas phase basicities can be are related to each other by just one minus sign. Again, when a conjugate base gets stronger, its gas phase basicity increases, its conjugate acid gets weaker, its gas phase acidity decreases, and vice versa. Another quantity to measure acidities and basicities is acidity function. Acidity functions like pH, Hammett acidity function, and so on are usually used for mediums, not alone compounds. And we will discuss them later in these tutorials. This is the end of this online tutorial. I hope you find it useful.